Hello there. Welcome to Just About Space. Close your eyes for a moment. Imagine yourself floating at the very edge of the known universe. Galaxies swirl like faint candle flames in the deep dark, each one so far away that their light has traveled for billions of years just to brush against your eyes. That light is the fastest messenger we know. It moves at just under 300,000 kilometers per second, a number so precise that textbooks carve it into their pages, as if it were the heartbeat of reality itself. For over a century, physicists have told us that nothing, not a spaceship, not a beam of information, not even a whisper from the future, can travel faster than this cosmic constant. It's the universal speed limit, the great boundary line drawn by the laws of physics. And yet, here's the thing. Every boundary in science has eventually been redrawn. Every so-called unchangeable truth in our understanding of the cosmos has, sooner or later, been questioned, shaken, or overturned entirely. So what if the speed of light isn't what we think it is? What if it has been lying to us? Or, more accurately, what if we have been lying to ourselves about its true nature? The idea might sound absurd. The speed of light isn't just a number. It's woven into the equations of Einstein's relativity, embedded in our definitions of time and space, even used to calibrate the very rulers and clocks by which we measure the universe. Changing it would be like pulling a single thread from an intricately woven tapestry. But throughout history there have been hints, tiny, almost imperceptible whispers, that light might not be as constant as we believe. Astronomers have spotted faint irregularities in how it travels across cosmic distances. Some theoretical physicists have dared to suggest that in the infancy of the universe, the speed of light could have been vastly different, and deep within the strange world of quantum mechanics, there are phenomena that seem to ignore its rules entirely. If these hints are true, then the implications are staggering. Physics, as we know it, could be incomplete. Our maps of the cosmos slightly, or perhaps catastrophically, wrong. Distances, timescales, even the age of the universe itself could shift beneath our feet. And yet, in the quiet corridors of research labs and observatories, this question continues to live in the shadows, always just out of reach of proof. Tonight, we two drift together into that shadow. We'll explore the history of the speed of light, where it came from, how we decided it was unbreakable, and why some scientists suspect the story isn't as solid as we've been told. We'll journey from Einstein's equations to the edge of black holes, from ancient starlight to the oddities of quantum entanglement. We'll meet the rebels of physics, the ones who dare to imagine a universe where light sometimes changes its pace, and where the cosmic speed limit is not a law, but a suggestion. You don't need to rush. Let each thought unfold like a slow wave. The universe will wait for us. The stars are patient. And as we begin, remember, in space, nothing is quite as constant as it seems. The story of the cosmic speed limit begins long before Einstein, long before we even had the instruments to measure light with any precision. For centuries, philosophers debated whether light traveled instantly or whether it had a measurable speed at all. The ancient Greeks split into camps over the matter. Empedocles suggested that light had to travel, and therefore must take time to cross space, while Aristotle argued that its motion was instantaneous. With no way to test it, the question lingered as a matter of opinion rather than science. That began to change in the 17th century, when an astronomer named Ole Römer, working at the Paris Observatory, noticed something strange while studying Jupiter's moons. He was timing the eclipses of Io, one of Jupiter's largest satellites, and found that the timing shifted depending on whether Earth was moving toward or away from Jupiter in its orbit. When Earth moved away, the eclipses appeared to happen later than predicted. When Earth moved closer, they happened sooner. Römer realized the simplest explanation: light takes time to travel, and as the distance between Earth and Jupiter changes, so too does the delay. From these shifts, he made the first rough calculation of light's speed. It wasn't perfect, but it was a beginning, the first crack in the idea of instantaneous light. In the centuries that followed, experiments grew more precise. In the mid-1800s, Fizeau and Foucault used rotating toothed wheels and mirrors to bounce light across known distances, measuring how long it took to make the journey. Each experiment chipped away at uncertainty, refining the number. By the late 19th century, physicists had established that light traveled at an astonishing speed, around 300,000 kilometers per second, and that this number didn't seem to change no matter how or where you measured it. Then came Einstein. In 1905, he published his theory of special relativity, a framework that would forever elevate the speed of light from a mere measurement to a universal constant. Einstein took the experimental evidence of his time and built upon it a daring premise. The speed of light in a vacuum is the same for all observers, regardless of their motion. Whether you're hurtling toward a light beam at half the speed of light or drifting away from it, you will still measure its speed as exactly say, no faster, no slower. This was not just a quirky detail. It became the cornerstone of a new understanding of reality. From it flowed the idea that time and space themselves are not rigid but flexible, stretching, bending, and twisting to preserve the constancy of light's speed. In relativity, this constancy is why we can't outrun a photon, why faster-than-light travel creates paradoxes, and why causality, the very ordering of cause and effect, is preserved. The number itself, c, became one of the most important constants in physics, alongside Planck's constant and the gravitational constant, and unlike most physical constants, it's not just a property of light, it's a property of space-time itself. Light merely reveals it to us. Any massless particle, whether it's a photon or a hypothetical graviton, will travel at this same universal rate. The speed of light is so fundamental that it is now baked into our definitions of measurement. In 1983, the meter was redefined not by a physical bar in Paris, but by the distance light travels in a vacuum, in exactly 1,299,792,458th of a second. The second, in turn, is defined by the oscillations of cesium atoms. This means that our very rulers and clocks are constructed around the idea that c is fixed and unchanging. It's not just a speed anymore. It's the scaffolding of reality as we've built it. And yet, the more we enshrined the speed of light as absolute, the more pressure it came under from the edges of science. Even in Einstein's lifetime, questions bubbled up. Quantum mechanics began to take shape in the 1920s and 30s, bringing with it bizarre phenomena that didn't seem to care about relativity's limits. Particles in quantum entanglement appeared to influence one another instantaneously, no matter how far apart they were, a spooky action at a distance that made Einstein himself uneasy. If information could, in some sense, be shared faster than light, what did that mean for the supposed speed limit? Astronomy, too, added its own puzzles. Light from distant galaxies is redshifted, stretched to longer wavelengths, not just because they're moving away from us, but because the very fabric of space between us is expanding. Over cosmological distances, this can make galaxies appear to recede faster than light without technically breaking the rules of relativity. And yet, to an observer, it challenges the intuition that c is an insurmountable barrier. Despite these edge cases, the official stance of physics has remained in a vacuum. The speed of light is constant and cannot be exceeded by any signal or particle. It's the bedrock of modern physics, the thing that holds the equations together. To deny it is to court scientific heresy. But science, if it is to remain honest, must always entertain the possibility that our bedrock is not as unshakable as we believe. Because what happens if we discover that light is not truly constant? If it has changed over time or varies under certain conditions, or if something else, some deeper law, governs its speed? Suddenly, every distance we've measured to the stars, every estimate of the universe's age, every calculation in our models would need to be revisited. The ripples would spread from astronomy to cosmology to quantum physics, tearing through our understanding like a quiet but relentless tide. For now, the cosmic speed limit stands. It is a law that has survived every direct test thrown at it. But the universe is vast, and and we have barely begun to sample its full variety. Somewhere, perhaps in the light of an ancient galaxy or the flicker of a particle we have yet to detect, there may be evidence that tells us the limit is not what it seems. And that's where our journey turns next, into the cracks that have already begun to show in this constant we thought unbreakable, into the whispers from theory and observation that suggest the speed of light might not be a cosmic decree, but a cosmic habit, one that the universe is capable of breaking. For most of the 20th century, the speed of light seemed untouchable. Experiment after experiment confirmed its constancy to more decimal places than anyone could count in their head. It became a sacred number, not just a speed, but a pillar on which the entire cathedral of modern physics was built. And yet, there were moments, subtle and quiet, when the data didn't quite fit the neat frame we'd made for it. Little shifts, small anomalies, the kind of details that most scientists filed away under instrumental error or not statistically significant. The polite graveyard where inconvenient results are buried until someone decades later decides to dig them up again. One of the earliest whispers came in the mid-20th century, when astronomers were measuring the arrival times of light from distant stars. In theory, the photons from these stars should behave predictably, their travel time determined by the vast but calculable distances between them and us. But certain measurements hinted that, under extreme conditions, light might arrive slightly earlier or later than expected, even after accounting for gravitational lensing or interstellar dust. Most dismissed these discrepancies as errors in observation, but to a few they hinted at something deeper, a suggestion that the speed of light might not be perfectly constant across space and time. In the 1990s, the conversation became louder, though still confined to the edges of the scientific community. João Miguel, a Portuguese cosmologist, began to explore an idea that would have been unthinkable in Einstein's day, that the speed of light might have been vastly different in the early universe. His proposal, the variable speed of light (VSL) theory, suggested that in the universe's first moments, light could have traveled much faster than it does today. This, he argued, could explain certain puzzles in cosmology, like the horizon problem, the question of how different regions of the universe, too far apart to exchange light at the current speed, seem to have reached the same temperature. The theory was bold, almost reckless. It implied that c is not a universal constant at all, but a number that changes depending on the epoch of the universe. If true, it would mean that our current measurements are just a snapshot of a value that has been shifting over cosmic time and might shift again in the future. The backlash was immediate. To most physicists, VSL wasn't just controversial, it was dangerous, because it struck at the heart of relativity. But to a small minority, it was exciting. It was a reminder that even the most sacred numbers in science should not be beyond question. Around the same time, other kinds of cracks began to appear, ones not tied to ancient history, but to the here and now. In certain high-energy particle physics experiments, hints emerged that some processes might involve signals that effectively exceed the speed of light, at least from our perspective. For example, in the study of quantum tunneling, where particles seem to vanish on one side of a barrier and reappear on the other without crossing the space in between, some measurements suggested that the effective speed of this process was faster than c. The mainstream interpretation quickly clarified that this didn't involve any actual transfer of information faster than light, thus preserving Einstein's sacred rule. But still, the mathematics had to be bent in curious ways to make the picture fit. Then came the quantum entanglement experiments, the ones Einstein famously derided as spooky action at a distance. In these experiments, two particles become linked in such a way that measuring the state of one instantly reveals the state of the other, no matter how far apart they are. The correlation happens with no detectable delay. To the human mind, that sounds an awful lot like faster-than-light influence. Physicists insist that it's not, that entanglement doesn't transmit usable information, and therefore doesn't violate relativity. But to a layperson, or to a philosopher of science, It feels like an invisible hand reaching across the cosmos in an instant. Even in astrophysics, the data sometimes seems to flirt with the edges of the limit. Observations of gamma-ray bursts, colossal explosions in distant galaxies, have revealed that high-energy photons sometimes arrive fractionally earlier or later than lower-energy ones. This could be the result of interactions with the quantum foam of space-time, as some theories suggest, or it could hint at something more radical, that the speed of light might vary with its energy. If that's the case, then c is not a single unbreakable value, but a curve, one we've only begun to map. And then there are the most controversial hints of all, the ones that spark heated debates in conference hallways and often never make it into journals. In 2011, the UPRA experiment in Italy briefly made headlines when it reported that neutrinos, those ghostly, nearly massless particles, had apparently traveled faster than light between CERN in Switzerland and the Gran Sasso laboratory in Italy. The claim was explosive, the implications seismic. If verified, it would have shattered the speed limit once and for all, but within months the result was traced to a loose fiber optic cable in the experimental setup. The speed of light was safe for now. Still, the incident was a reminder that our certainty rests not only on theory, but on the fragile machinery of measurement. Taken together, these moments form a strange constellation. Each point on its own is not enough to change the map of physics, but connect them, and a faint outline appears, the shape of a possibility that the speed of light is not the fixed, eternal constant we have imagined it to be, but something more subtle, something that changes with time, space, energy, or even with the hidden geometry of reality itself. The cracks in the constant are not yet breaks. They may close again with better data, or they may widen into chasms that force us to rebuild our understanding from the ground up. For now, they remain as invitations to curiosity, to humility, to the willingness to ask dangerous questions. And so, with those cracks in mind, we turn to the theories that dare to imagine a universe where light is not bound by a single immutable speed, theories that treat c not as a sacred number, but as a variable, shifting across the history of the cosmos, like the beat of a living heart. If you tell most physicists that you think the speed of light might not be constant, you will often get a look somewhere between polite amusement and outright suspicion. In modern science, challenging c is a little like walking into a cathedral and suggesting that maybe the altar is in the wrong place. But there have always been those who are willing to ask the question anyway, and a few have even tried to build entire theories around it. These theories fall under a loose banner, variable speed of light, or VSL for short. The central idea is simple enough to state: the speed of light, rather than being fixed for all of time, could have been different in the past, might vary under certain conditions, and could even change in the future. The implications are not simple at all. If c can change, then the equations of relativity, and by extension much of modern cosmology, would have to be rewritten from the ground up. One of the earliest and most provocative champions of VSL was Joao Magejo, a cosmologist whose work in the late 1990s and early 2000s stirred both fascination and outrage. He wasn't setting out to cause trouble for Einstein. He was trying to solve a genuine puzzle in cosmology known as the horizon problem. Here's the problem in plain terms. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see that it's remarkably uniform in temperature across the sky. The trouble is, according to the standard Big Bang model, many of these regions are too far apart for light to have traveled between them in the age of the universe. Without that exchange of energy, there's no way for them to agree on a common temperature. It's as if you walked into a huge room where everyone was wearing the same color shirt, but no one had ever met or spoken to each other. The inflation theory, a rapid exponential expansion of space in the first fraction of a second after the Big Bang, is the mainstream explanation for this. But Magejo proposed an alternative. What if in those first moments the speed of light was much, much faster? If light could cross the young universe more quickly, it could easily smooth out temperature differences without requiring an inflationary burst. This variable speed idea could also help with other puzzles like the flatness problem, the question of why the geometry of the universe is so close to perfectly flat. The reaction to Magejo's work was mixed. Some saw it as an elegant alternative to inflation, worth exploring for its own sake. Others dismissed it as a kind of heresy, an unnecessary complication when inflation already fit the data. Magejo himself described the pushback in almost cultural terms, as if he had offended a deeply held scientific faith, but the idea didn't disappear. Other researchers began exploring their own versions of VSL, tweaking the equations of relativity so that C could vary without breaking the rest of the mathematical machinery. Some models proposed that C is tied to the properties of the vacuum, and if the vacuum itself changes over cosmic time, so too would the speed of light. Others suggested that C might depend on energy scales so that high-energy photons could travel slightly faster or slower than low-energy ones over vast distances. This kind of energy-dependent speed is tantalizing because it could, in theory, be tested by observing the arrival times of different photons from the same astrophysical event, like a gamma-ray burst. There are even speculative ideas that link changes in the speed of light to deeper, more exotic features of the universe's structure. In some approaches to quantum gravity, the still elusive theory that would unite general relativity with quantum mechanics, space-time itself might be grainy at the smallest scales like pixels on a screen. If light interacts with this microscopic texture, it might experience tiny variations in speed depending on its wavelength, polarization, or direction of travel. Over billions of light years, those tiny variations could accumulate into something measurable. Perhaps the most unsettling version of VSL is one that ties it to the constants of nature as a whole. In physics, we often talk about numbers like the fine structure constant, which governs the strength of electromagnetic interactions, or the gravitational constant, which controls the strength of gravity. If one of these constants varies over time, it's possible, perhaps even likely, that C would vary as well. In that scenario, the speed of light is not just a standalone property, but part of a web of relationships that shift together as the universe evolves. Of course, there's a reason most physicists tread carefully here. Letting C vary is not like tweaking a minor detail in an equation. It changes the entire playing field. It forces you to rethink causality, time dilation, energy conservation, and the relationship between space and time. A universe where C changes could allow for phenomena we currently consider impossible faster than light travel without paradox, signals from the future, or even new ways to manipulate space-time itself. That's thrilling and terrifying. There's also the challenge of evidence. If the speed of light really does vary, it would have to do so in a way that's consistent with the overwhelming precision of our current measurements here and now. That means either the variation happened only in the deep past, or it's so subtle today that it hides in the noise of our instruments. Detecting such a change would require extraordinary accuracy, long-term monitoring, and a way to disentangle any variation in C from all the other cosmic effects that can delay or distort light. Still, the lure of VSL persists, partly because it reminds us of an uncomfortable truth. Our most fundamental constants are only as constant as the universe allows them to be. They are numbers we have measured, yes, but they are also numbers we have assumed will never change. And history is full of moments when such assumptions have fallen apart. So the question lingers in the background: if the universe has the power to bend time and space, to stretch the fabric of reality itself, why should we believe it has forever chained the speed of light to one unchanging value? In the next part of our journey, we'll dive into a realm where the speed of light is not just challenged by alternative cosmologies, but seemingly ignored by nature itself, the strange, mind-bending territory of quantum mechanics, where particles can be connected across the void and where speed becomes a slippery, almost meaningless word. If the story of the speed of light were told only in the language of classical physics, it would be clean, almost comforting. A single number, fixed and absolute, defining the maximum pace at which anything can move. But step into the quantum world, and that comfort evaporates. In this strange realm, the concept of speed starts to lose its meaning, and with it, the very idea of a universal speed limit begins to feel like a polite illusion. The trouble begins with quantum entanglement, a phenomenon that even Albert Einstein, the man who gave us chi as an absolute, found deeply unsettling. In the 1930s, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper describing what would later be called the EPR paradox. They imagined two particles that interact in such a way that their properties become perfectly linked or entangled. Once separated, measuring the state of one particle would instantly determine the state of the other, no matter how far apart they were. To Einstein, this smelled of something incomplete in quantum theory. He called it spukhaft Fernwirkung, spooky action at a distance. If the effect were real, it seemed to imply that information could travel faster than light, violating the bedrock of relativity. Quantum physicists, however, insisted that entanglement didn't actually transmit usable information faster than light. Rather, it revealed correlations that were set up when the particles were created. In their view, the universe wasn't breaking the speed limit, it was simply playing by rules we didn't fully understand. But here's the thing. The practical difference between instantaneous correlation and faster-than-light influence is murky. In the decades since, experiments have confirmed that entanglement is real and robust. Bell's theorem, formulated in the 1960s, provided a mathematical way to test whether these correlations could be explained by hidden variables traveling at or below c. The experiments showed they could not. The universe really does seem to allow a kind of connection that ignores distance, a link that is, for all practical purposes, instantaneous. For someone lying in bed at night thinking about the stars, this feels like a loophole in the cosmic speed limit. If two particles can know about each other instantly, why can't we use that to send a message faster than light? The answer, frustratingly, is that quantum mechanics seems to guard against this in a way that defies common sense. You can share entanglement, but you can't use it to transmit meaningful information without also sending a classical signal, which is bound by c. It's like having a magical telephone that lets you sense when the other person picks up, but doesn't let you actually speak. Still, entanglement is not the only quantum oddity that pokes at the edges of the speed of light. Consider quantum tunneling. In the classical world, if a ball doesn't have enough energy to roll over a hill, it stops. In the quantum world, a particle can simply appear on the other side of a barrier without crossing it in the usual sense. This tunneling is a consequence of the probabilistic nature of quantum mechanics. Particles are described by wave functions that can extend into regions that should be forbidden, and sometimes those extensions manifest as actual crossings. In certain experiments, the effective tunneling time appears to be so short that if you calculated a speed, it would exceed c. Physicists again caution that no real signal is traveling faster than light here. What moves is a probability wave, not a tangible object carrying information. And yet, to the curious mind, these careful distinctions start to sound like the rules of a game written to protect an old law, rather than an honest description of how the universe behaves. Even light itself is not immune to quantum strangeness. In a vacuum, photons travel at c, but put them through certain materials and they can slow dramatically, a trick used in laboratory experiments to bring light to a crawl. Conversely, through clever manipulation of refractive indices, scientists have created conditions in which the group velocity of a pulse of light appears to exceed c. Again, the official line is that this does not involve any faster-than-light transfer of information, but the fact remains our everyday definition of speed becomes slippery in the quantum domain. There's also the question of virtual particles, the ephemeral carriers of forces in quantum field theory. These particles flicker in and out of existence in such short intervals that they defy the normal constraints of speed and energy, borrowing against the uncertainty principle in ways that, if taken literally, would seem to ignore the cosmic limit entirely. In some interpretations, these are just convenient mathematical tools, not physical entities. In others, They are as real as anything else in the quantum vacuum. And if they are real, they behave in ways that make C look less like a wall and more like a guideline. Perhaps the most intriguing intersection of quantum mechanics and the speed of light comes from attempts to merge it with general relativity. In the search for a theory of quantum gravity, some approaches, like loop quantum gravity or certain versions of string theory, suggest that space-time itself has a discrete, granular structure at the Planck scale. If this is true, then over incredibly long distances, light's interaction with this space-time foam could lead to tiny variations in its speed, depending on energy or polarization. High-energy photons from distant gamma-ray bursts, for example, might arrive slightly earlier or later than lower-energy ones, hinting at a subtle breakdown of the constant speed rule. For now, none of these quantum quirks have led to a definitive overthrow of C as the ultimate limit. The physics community maintains that relativity still stands unbroken, that quantum mechanics works alongside it without actually crossing the forbidden line. But if you step back and look at the patterns, you see something interesting. Again and again, nature seems perfectly comfortable with phenomena that skirt the edge of the speed limit, brushing against it in ways that our theories must carefully explain away. It's as though the universe is telling us two things at once. On one hand, yes, the speed of light is the limit, and nothing will ever surpass it in the way you think. On the other, but speed is not as simple as you imagine, and the deeper you look, the blurrier your definitions become. In the next section, we will step out of the laboratory and into the vastness of the cosmos, where the geometry of space-time itself can play tricks on our understanding of speed, where light can be bent, delayed, or apparently overtaken, not because it has broken the rules, but because the rules themselves are written on a shifting canvas. Stand outside on a perfectly clear night, far from city lights, in the stillness of a high desert or the black quiet of a mountain plateau, and look up. The stars seem frozen, like tiny beads pinned against a velvet dome. It feels almost static, but in truth, you are looking into a universe in motion. Every single one of those points is racing along its own path, carried on invisible currents of space-time itself. And hidden within those motions is a subtle trick, the appearance that the speed of light, our cosmic speed limit, is not always obeyed. The first of these tricks comes from the expansion of the universe. Since the 1920s, when Edwin Hubble first observed that galaxies are moving away from us, we've known that the fabric of space is stretching. It's not that galaxies are flying through space like shrapnel from an explosion. It's that the very stage on which they exist, space-time itself, is growing. And here's the strange part. When space expands, it can carry objects apart at an effective speed greater than the speed of light without violating Einstein's rules. The key is that relativity's speed limit applies to motion through space, not to the stretching of space itself. Imagine two ants sitting on a balloon. If the balloon inflates slowly, each ant might walk across the surface at a certain pace. But if the balloon suddenly stretches faster than they can walk, the ants will find themselves farther apart, not because they moved faster, but because the space between them grew. On the cosmic scale, this means that a galaxy billions of light years away can appear to be receding from us at more than 300,000 kilometers per second, yet still remain within the bounds of relativity. This has a startling consequence. There are regions of the universe from which light will never reach us, no matter how long we wait. Beyond a certain horizon, the expansion of space is so rapid that the light emitted toward us is effectively swept away faster than it can close the gap. From our perspective, those galaxies are already lost to time, receding into a darkness we can never cross. It feels like a violation of the speed of light, but it's really the geometry of space-time playing a sleight-of-hand trick. A second illusion comes from gravitational lensing, the warping of light's path by massive objects like galaxies or black holes. Einstein's general relativity tells us that mass curves space-time, and light follows those curves. To us, it looks as though the light is being bent, sometimes taking long, looping paths that make it appear to arrive later than it should, or, in rare cases, earlier than expected if the bent path happens to be shorter than the straight one we'd imagine. These gravitational detours can give the impression that light's speed has changed, when in reality it's just taking a winding road across the cosmic landscape. But lensing can do more than bend light. It can magnify and split it. A single distant galaxy might appear as multiple images in our telescopes, each one showing the galaxy at a slightly different point in time. In some extraordinary cases, the light from a supernova, an exploding star, has been bent in such a way that we see the explosion before and after it happens, as different paths of light converge on us from different angles. The time gaps here are a reminder that speed in the universe is not just about how fast light moves, but about how the shape of space-time shapes our experience of it. Then there's the Doppler illusion, familiar from sound but equally relevant to light. When a source of light moves toward us, its waves are compressed, shifting toward the blue end of the spectrum. When it moves away, they're stretched toward the red. In extreme cases, like the jets of particles ejected from the regions around black holes, this can create the appearance of superluminal motion. We've actually observed galaxies whose jets seem to be moving many times faster than the speed of light. The reality is that these jets are moving very close to C, and they're angled toward us in such a way that their apparent speed across the sky is an illusion of perspective and timing. It's a trick of geometry, not a cosmic law being broken. Even more puzzling are phenomena tied to the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in its temperature and polarization tell us about the structure of the early universe. But to interpret them, cosmologists have to account for the fact that light has been stretched and delayed in ways that can make its journey seem inconsistent with a single fixed speed. The expansion of space, gravitational wells along the way, and even the subtle tug of dark energy all conspire to warp our perception of how fast that light has really traveled. Perhaps the most poetic illusion of all is time dilation near massive objects. At the edge of a black hole, time itself slows relative to an outside observer. A photon climbing out of that gravitational well still moves at c locally, but from our perspective its escape is drawn out, redshifted and weakened, as if it were struggling against the rules. Stand on the brink of an event horizon, and the outside universe would seem to race ahead while you linger in slow motion. To someone watching you from afar, your last moments would stretch toward infinity, your final photons crawling away at a pace that seems to defy the constant speed we've sworn to. All of these effects, expansion, lensing, Doppler illusions, time dilation, conspire to make the speed of light feel less like an unyielding wall and more like a shifting mirage. In every case, relativity holds firm in the background, but the experience of light's journey becomes tangled with the shape and behavior of space-time itself. This raises an unsettling question. If our perception of light speed can be so easily distorted by the universe's geometry, how certain can we be that our measurements here and now reflect some deep eternal truth? Could it be that our constant is a kind of local rule, true in our neighborhood but different elsewhere? Or are we simply seeing the cosmic stage from the wrong angle, mistaking its moving parts for a change in the play? In the next section, we'll leave illusions behind and step into the hard edge of measurement, the experiments designed to push the boundaries of C, to catch even the slightest deviation from its sacred value. Because if the speed of light really does change, somewhere, sometime, we should be able to catch it in the act. If there is a chink in the armor of light's supposed constancy, it will be found not in philosophical debates or poetic illusions, but in the quiet, meticulous work of measurement. The universe is vast, but physics is built in the laboratory, in rooms where the air hums faintly from cooling fans, where vibration-isolated tables hold delicate machinery, and where scientists chase differences so small they're measured in billionths of a second. This is where the speed of light's reputation is either confirmed or begins to crack. The idea of measuring light speed with absolute precision dates back to the 19th century, When scientists like Fizeau and Foucault devised clever rotating mirror setups to time its journey across a few kilometers, those experiments, though primitive by today's standards, gave answers remarkably close to the value we now use. But as the decades passed, our ability to measure improved, and so did the expectations. By the late 20th century, measurements of C were accurate to parts per billion. Any variation, if it existed, would have to be exquisitely small. The gold standard for modern tests is interferometry. In an interferometer, light beams are split, sent along different paths, and then recombined to produce interference patterns, a delicate pattern of bright and dark fringes. If the speed of light along one path changes by even a fraction, the interference fringes shift. Interferometers are so sensitive that they can detect changes smaller than the diameter of a proton. The most famous example is the Michelson-Morley experiment of 1887, which sought to detect differences in light speed caused by Earth's motion through the hypothetical luminiferous aether. The result was null, no detectable difference, and that null result helped pave the way for Einstein's relativity. Today, interferometers like those used in gravitational wave observatories, LIGO and Virgo, are pushing this sensitivity even further. These massive instruments, with arms stretching kilometers, are designed to detect space-time ripples from colliding black holes, but they also offer opportunities to test whether light speed is perfectly stable over time, direction, and frequency. So far, the answer remains a steady yes, at least within the limits of our instruments. Another frontier is astrophysical timing. Certain cosmic events act as natural laboratories for testing the invariance of C. Take gamma-ray bursts, brief, intense explosions in distant galaxies. They release photons across a wide range of energies all at once. If the speed of light varied with photon energy, we would expect high-energy photons to arrive at Earth slightly earlier or later than low-energy ones. After traveling billions of light years, sensitive telescopes like the Fermi Gamma-Ray Space Telescope have looked for such delays. The results so far? No confirmed deviation, but the data always leave a little room for something subtle, hidden below the noise floor. We also have pulsars, spinning neutron stars that emit beams of radio waves like cosmic lighthouses. These pulses arrive with incredible regularity, sometimes more stable than our best atomic clocks. By timing them over years, astronomers can check whether the apparent speed of their signals changes with the seasons, the motion of Earth, or other factors. Once again, no variation has been definitively detected, but these long-term data sets are precious, because even the smallest drift could be a clue. Then there are the laboratory constants tests, where scientists monitor the relationship between C and other physical constants, like the fine structure constant alpha. If alpha changes over time, it could imply that C is shifting too. Certain high-precision spectroscopy experiments, which compare the absorption lines of different atoms over months or years, have hinted at possible variations in alpha. But the evidence is mixed and hotly debated. Critics argue that temperature changes, magnetic fields, or equipment calibration errors could explain the signals. Proponents counter that the hints are consistent across multiple experiments in different countries. The most controversial direct measurement attempt in recent decades came in 2011 with the Opera neutrino experiment, which seemed to find that neutrinos from CERN arrived at the Gran Sasso laboratory 60 nanoseconds faster than they should have if they traveled at C. The announcement sent shockwaves through physics, because if neutrinos could exceed light speed, relativity would be in serious trouble. Within months, the anomaly was traced to, of all things, a loose fiber optic cable and a faulty oscillator in the timing equipment. The result was quietly withdrawn, and the cosmic speed limit returned to its pedestal. But the incident was a reminder of how delicate these measurements are, and how easily a small oversight can masquerade as revolutionary physics. Even so, the pursuit continues. New ideas keep emerging for space-based tests that could surpass Earth-based precision. Imagine a pair of satellites separated by millions of kilometers, linked by laser beams, able to check for differences in C over vast distances and in different gravitational potentials, or observatories parked on the far side of the moon, shielded from Earth's radio noise, using deep space signals to probe for minute deviations. Some researchers even propose using quantum entanglement experiments stretched across Earth-Moon distances to test whether C is truly inviolate. Yet, for all this ingenuity, one thing is certain: if the speed of light is variable, it hides well. It hides in a way that is either so subtle that our best instruments barely graze it, or so rare that we have yet to witness the conditions under which it changes. This leads some to suspect that perhaps it doesn't vary at all, that every anomaly, every crack we think we see, is just a mirage caused by noise, misinterpretation, or incomplete data. But science doesn't move forward by defending constants. It moves forward by testing them. The absence of evidence is not evidence of absence. We are, after all, still in the earliest chapters of precision cosmology. Instruments will get better, baselines will get longer, timing will grow sharper. And if C has a secret, if there is even the smallest place in the universe where light dares to break its own rule, then sooner or later the numbers will betray it. In the next section, we'll step away from the lab and allow ourselves to ask the speculative question: what if the limit actually breaks? What if tomorrow a measurement comes in that is undeniable? What happens to physics, to causality, to our understanding of time itself when the cosmic speed limit is no longer absolute? Imagine the scene. Somewhere, in a quiet underground laboratory, in a space telescope's data stream, or perhaps in the chatter of a deep space probe, a measurement comes in that cannot be ignored. It is checked, rechecked, run through every filter and calibration protocol, compared against every possible source of error. And yet, it stands. A signal, a particle, a pulse of light has moved faster than the cosmic speed limit. The news would not arrive with the dramatic flourish of science fiction. No warp drives igniting in orbit, no sudden rush of ships to other star systems. It would begin as a paper, dry, cautious, and heavily footnoted, but heavy with implication. Physicists would swarm it, skeptical and hungry in equal measure. Some would tear it apart, searching for flaws. Others would begin sketching equations on whiteboards, reimagining space and time from first principles. The first and most immediate consequence would be to causality, the deep ordering principle that tells us effects follow causes. In relativity, the speed of light is not just about motion, it's about the very architecture of space-time. It defines the light cone, the boundary between events that can influence each other and those forever separated. Break the limit, and the cones blur. Suddenly, in some frames of reference, an effect might be seen before its cause. Information could, in principle, loop back in time. Paradoxes would no longer be just thought experiments. They would become engineering problems. Some physicists would argue that faster-than-light travel does not necessarily mean time travel, that clever frameworks might preserve causality even if C is exceeded. These ideas exist already in certain corners of theoretical physics, in concepts like tachons, hypothetical particles that always move faster than light, or in warp-metric solutions to Einstein's equations, like the Alcubierre drive, which stretches space rather than moving through it. But even these solutions are carefully crafted to tiptoe around paradox. A real, unambiguous measurement of something outrunning light would force the conversation out of the theoretical and into the practical. Technology, of course, would become the focus almost immediately. The dream of interstellar travel, once confined to slow arcs measured in centuries, would suddenly flicker into the realm of possibility. Engineers and visionaries would ask, if a particle can do it, can a spacecraft? Could we ride whatever mechanism nature has revealed, using it as a shortcut across the abyss between stars? Entire industries would be born around the pursuit, and billions would be spent chasing prototypes. But the road from particle physics to starships is long, and the physics that allows faster-than-light motion, for one thing, might slam shut for another. Even without ships, the ability to send information faster than light would change everything about communication. We could speak in real time with colonies around other worlds, coordinate space telescopes on opposite sides of the galaxy, send probes into the void and receive their findings instantly. But here again, the ghost of causality lurks. If information can arrive before it's sent, from the perspective of some observers, the fabric of cause and effect phrase, this is not just a scientific issue, it's a philosophical one. Our very sense of before and after could lose its universal meaning. The implications for physics itself would be seismic. Special relativity, one of the most tested and trusted theories in science, would need revision, not discarded but expanded to include conditions where the limit no longer holds. General relativity, too, would have to accommodate this new reality, and quantum field theory, our most precise description of the subatomic world, would need to explain how a speed limit can be broken without violating other sacred principles like energy conservation or the stability of the vacuum. Entire careers would be spent building post-relativity frameworks, hunting for the deeper law that makes C an approximation rather than an absolute. Cosmology would face its own upheaval. Distances to galaxies, the age of the universe, and the dynamics of cosmic expansion are all calculated with chi as a constant. If it changes, even slightly, those calculations must be revisited. Our cosmic map might shift in ways we can't yet imagine. Perhaps the universe is older or younger than we think. Perhaps the early cosmos behaved in ways we have misread. Faster-than-light phenomena could also provide new ways to probe regions currently hidden from us, like the interiors of black holes or the moments before the cosmic microwave background was released. And then there's the human response. We tend to treat speed as a measure of freedom. The faster you can go, the more of the world you can reach. But in a universe where faster-than-light motion is possible, that freedom comes with disquieting possibilities. Messages from the future, events without clear causes, the erosion of the one-way arrow of time that gives our lives structure. Some would embrace the new reality as a kind of cosmic liberation. Others would find it deeply unsettling, even dangerous. Laws and treaties might be written to govern the use of superluminal communication, to protect against time-violating technologies that could be abused. And yet, perhaps the most profound change would not be technological or political, but psychological. For over a century, the speed of light has been our one firm boundary in a universe otherwise full of unknowns. It's been the ultimate constant, the line we could never cross. If that line moves, even a little, it changes our relationship with the cosmos. It tells us that the universe is not finished revealing its rules, that the constants we've built our understanding upon are more like habits than laws. It reopens the possibility that reality is stranger, more fluid, and perhaps more alive than we thought. Of course, there is another possibility, one that's almost poetic in its irony. If the speed of light is broken, we may find that this freedom comes with limits of its own, that there is another boundary, further out, waiting to replace the old one. Perhaps every limit we discover is only a horizon, and beyond it is another, and another still. In that sense, the breaking of K would not be an end, but a continuation of the same story, the one we've been telling since the first time we looked up at the stars and wondered how far we could go. In the next section, we will step back from speculation and turn inward, asking why we are so drawn to the idea of cosmic limits in the first place, and what it means for us, as thinking beings, if one of those limits turns out to be a lie. There is something strangely comforting about limits. We often think of them as cages, restrictions that hem us in, but on another level, they are anchors. They give shape to the formless, edges to the infinite. A universe with no limits would be a kind of chaos, a place without reference points, where our ideas of near and far before and after dissolve into meaninglessness. And for more than a century, the speed of light has been one of those anchor points. It is not just a number in the physics textbooks. It is a promise. a promise that no matter how vast or varied the cosmos may be, there is a maximum pace at which change can ripple through it. It's the invisible metronome of the universe, ticking off the beat of causality. Without it, our sense of time itself would lose its steady pulse. But here's the paradox. We are explorers by nature, and explorers are rarely satisfied with the edges they are given. We want to know what lies beyond the map, beyond the rules, beyond the fence posts planted by nature herself. Every generation, we find a way to push past what the last generation thought was absolute, to redefine what possible means. The speed of light, in that sense, has always been a kind of challenge in disguise. It stands there in our equations, like a mountain in the distance, daring us to climb, and even if we never reach the summit, the act of trying teaches us something about the landscape. This is why I think we keep circling back to the question of whether c is really constant. On the surface, it's a technical question for physicists and cosmologists, but beneath it lies something more human, a need to test the walls of our reality, to find the seams in the fabric and see if they can be pulled. We may never travel to another galaxy, but the knowledge that it might be possible someday changes the way we see the night sky. It turns the stars from distant decorations into destinations. And yet there is a deeper, more subtle reason we fixate on this cosmic speed limit. It has to do with the way we think about truth. Constants like c feel eternal. They are supposed to be the same yesterday, today, and tomorrow. If they change, then truth itself becomes something more like weather than bedrock, shifting, seasonal, and context-dependent. That can be liberating, but also deeply unsettling. Perhaps that is why the possibility of a variable or breakable c feels almost poetic. It suggests that the universe is not a finished sculpture, cold and fixed, but a living process, something that can evolve, adapt, even surprise itself. In that view, the speed of light is not the final word on motion, but simply the fastest pace the cosmos is willing to allow right now. Tomorrow, or a billion years from now, the answer might be different. It also reminds us of our own changing limits. Every human life has its constants, the things we think will always be there, the faces we expect to see when we wake up, the habits we believe will define us forever, and yet time proves otherwise. People change, circumstances shift. What felt like a fixed boundary one year can dissolve the next. In that way, the speed of light is a kind of metaphor for our own lives. Even the most solid-seeming rules can turn out to be temporary. The irony, of course, is that in physics, constants give us a kind of power. They make the universe predictable, calculable, something we can navigate and engineer around. If C were to vary wildly, building a working technology, let alone a civilization, would be far more difficult. So we live in a strange tension. We crave the stability that constants offer, but we also itch to see them broken. And maybe that sips the heart of it. We don't actually want a universe without limits. We just want limits that are negotiable, rules that can be bent if you know the trick, horizons that can be crossed if you are willing to go far enough, a cosmos that says, you can sit yet. The poetic horizon, then, is not the line where the sky meets the earth. It is the boundary between what we believe is fixed and what might be revealed as fluid. The speed of light is one such boundary, a glowing, invisible circle around our understanding. Whether it stands forever or one day falls, its existence gives us something to work against, to dream beyond. And so, whether the speed of light turns out to be a lie, a half-truth, or a perfectly unshakable fact, it will always have value. It will always be the spark that keeps us looking upward, questioning, wondering what other constants might one day prove to be not constants at all. In the next section, we will begin winding down this journey, gathering the threads of history, theory, experiment, and imagination, and step into the calm, reflective conclusion of our exploration, a place where the stars are still, the universe is quiet, and the question of speed gives way to the deeper question of understanding itself. So here we are, We've drifted from the laboratories of Earth to the farthest horizons of the observable universe, tracing the long arc of a single number, 299,792,458 meters per second, and the questions that cling to it. We've seen how it became our cosmic yardstick, how it anchors the laws of physics, and how in certain corners of theory and observation, the edges of its perfection begin to fray. Along the way, we've met the dreamers and the skeptics, the scientists who have spent decades confirming that C never wavers, and the rebels who have dared to imagine a universe where it does. We've wandered through the illusions of cosmic expansion, the strange shortcuts of quantum mechanics, and the philosophical tension between needing limits and wanting to break them. And yet, after all this, the speed of light remains what it has been for over a century. The most trusted constant in science. Every measurement, every test, every probe of deep space has found it unshaken. If it has secrets, they are buried deep, too deep for our current tools to uncover. But perhaps that's exactly the point. The mystery is not diminished by the absence of a crack. It is deepened by it. The act of trying to find its limits teaches us as much about ourselves as it does about the cosmos. It forces us to refine our instruments, to sharpen our ideas, to keep looking at the universe with both rigor and wonder. In the end, whether the speed of light is an eternal truth or a temporary habit of nature, it has already done something extraordinary. It has given us a way to measure not just distances in space, but the reach of our own curiosity. It's a reminder that even when a boundary holds, the journey toward it changes us. So tonight, if you find yourself under a sky clear enough to see the stars, remember, every point of light above you is a messenger, traveling at the cosmic pace we've come to call absolute. Some left their homes millions or even billions of years ago, crossing the darkness to arrive here now in this moment, to touch your eyes. They are proof that the universe is both constant and in motion, both bound by rules and filled with possibilities we've yet to name. And as long as there is a question about the true nature of that speed, there will be reason to keep watching, keep measuring, keep wondering, because the most important thing about a limit is not whether it can be broken, but the way it calls us to try. Good night.